Good morning, Sarthakji. Good morning.
Yes. Well, Swati,
Good morning. Good morning to invited speakers, faculties, and participants. It's my privilege to introduce a renowned academician, exceptional researcher, and visionary in the field of electrical and electronics engineering, Dr. Kumar Vaibhav Srivastav sir, professor at IIT Kanpur. Dr. Srivastav sir is widely known for his expertise in the areas of microwave engineering, metamaterials, and RF system. Over the years, he has made significant contribution to scientific community as well as in the academics and research. Sir has obtained his PhD from IIT Kanpur and has published in numerous reputed journals and conferences, many of which are widely cited and form the foundation for ongoing research in advanced communication system. Dr. Srivastav sir has also been actively involved in sponsor research projects in collaboration with ISRO, DRDO, DST, and MIT. Beyond his research achievements, Sir is known for his mentorship and academic leadership. Sir, we are truly fortunate to have you today with us. And now I request you to kindly take over the session and enlighten our participants.
Hi, good morning.
Good morning, sir.
Good morning to first thing I want to thanks to the Mr. M. Sharma who actually brought me on this platform and all the faculty member of the MNIT Allahabad as well as like the IEEE society which is actually also involved in this workshop. So the topic which is actually given to me is I've seen like that there are many sessions which are actually going on the MIMO antenna in this workshop. So what actually I feel like that this one is like the first one on the MIMO antenna which in this session. So I will try to cover more on the basic of the MIMO antenna, why actually like the MIMO antenna people are trying to use, and some of the example which actually has been developed by our group. So what actually I suggest like I don't know it is the webinar, but if some participant wants to ask us some question during the session, please allow them.
Sure, sir. We will allow them. Yes.
So if we go from this MIMO antenna, so first thing is like we have to understand like how the generation is actually changing. Generation is actually which is more about the data speed. We actually talk about like the from 3G, 4G, or the 5G, and the 5G it is given like whatever the data speed you can actually achieve is the 10 Gbps. Okay, as compared to like the 4G and the 3G, which was like the 100 Mbps and the 2 Mbps. So how we can actually achieve such the data speed, and the 6G is actually even like the predicted at the 100 Gbps. So we have to actually see like what are actually major factor which can achieve such a thing. So before going to this more on the what is the MIMO, let us first understand like in the 5G what is the data speed or how much data we are actually predicting in coming years. So 5G it says like currently close to like the 3 billion people are there, and by the 2029 we will have like the 5.3 billion people who will be actually using this 5G network, and the data which actually we are using on the internet, it will be actually close to like the 21 GB per month from the 2023 to the 56 Gbps, so 56 gigabyte by the 2029. So it is like the very huge data which we are actually expecting, and it is also like the 85% of the people by 2029 will have the 5G coverage. So this is like the one of the way like the people are predicting the 5G or the coming 6G. It is like the way we have connected our network devices that will be huge. Earlier, mostly like we were using this data communication with the mobile, but now like everywhere we are using like whether we have this wristwatch, which is actually like the smartwatch, which actually connected with the server, or we have the vehicle which is connected, or any home or the home appliances are connected. So many things are actually connected, and because the most of the people are connected through internet, with the various machines, you need the huge data sharing. So if we go from the, I will focus more about the from the 4G to 5G or the 3G to 4G, the technology is actually significantly changing. So in 4G, the major contribution which actually provides the higher data speed is actually like the MIMO antenna, which is like the multiple input, multiple output antenna. Whereas in the 5G, we have massive MIMO antenna, which will be uh, participating to increase your data speed. So there is like the MIMO antenna, which is anyway, it was actually there in the 4G, but it is massively are using in the 5G, and 5G, though it is the technology proposed for the massive MIMO, but it's still like the number of the MIMO elements which we are using is still limited. We'll cover like the what is like the meaning of the MIMO and what is like the massive MIMO. But the way we actually increase or enhance our data speed in the 4G or the 5G network, that was like the first one was like the MIMO antenna. Like the on the transmitter side, you have the many number of the antenna, and the receiver side also you have the many number of antenna, and the transmission actually take place. The second one is like the adaptive beam forming, where you actually form the beam in the particular direction, like the from the base station to the user, you can have like the beam which will actually form, and this beam forming network will be actually like the changing as per the requirement, and that's why the word is the adaptive beam forming. Then we have the advanced modulation and the coding scheme, then the multiple access. Then another one is like the smaller cell, which is like it could be like the pico cell or the femto cell, and then we'll have the millimeter wave uh, thing. So, but the even the 6G, we are not actually planning to go for the millimeter wave. It will again be like the close to like the 7 to the 13 gigahertz in that frequency range it may come. So we are still like the electronics or the exchange are still not ready to cater the demand for the millimeter wave application. But this, people are actually predicting that will actually enhance our data speed. So what actually happening here, just let me see that if I can take the laser. Yeah, so in MIMO antenna, what happened like the let's say you have the stream of the data which is there. So if you want to transmit through the MIMO system, you will actually receive it from the your source, and then you actually convert those data stream from the serial to parallel converter. So you will have the streams which there's a huge data is there, but you will actually convert it from the serial stream to the parallel stream. You encode them, you modulate them, and then you actually transmit with the antenna. And now if you see that these are actually like the transmitting side, so you have like the more number of the antenna which are actually transmitting, and similarly on the receiver side, you will have the more number of the antenna, like the more than like the one antenna which is actually transmitting, which is receiving the signal. Then you will do the some signal processing at the just after the antenna, demodulate the signal, decode, and the parallel to serial converter, and then the data is actually out over here. So this part is actually like the this MIMO system which is actually participating, and the MIMO antenna system which I will actually say which is actually giving. So first thing is like that there are the multiple antenna which are used on the both transmitter and the receiver sides to increase, and it says like that different signal are transmitted out of the each antenna simultaneously and then the same bandwidth. So these two are very important. Like the all the antenna are operating simultaneously. Like if we see this our let's say like this mobile handset, we have already the multiple antenna, but they don't transmit simultaneously, or they don't operating in the same frequency band. Like let's say like if you are having the on the mobile handset, you have the GPS antenna, you have the Wi-Fi antenna, you have the antenna which is connected with the base station, then you have the Bluetooth antenna, but they all are either not operating on the same frequency, or they all are not operating in the simultaneously. So what MIMO antenna says like that if you have the multiple antenna, they all are transmitting simultaneously and in the same bandwidth. So that is very important. If you say like that these antennas are actually like the MIMO antenna. And this, so now if you think of like the, because we are actually converting the serial to the parallel data stream, so all the data which are actually going towards like this receiver side, they are actually having the good number of data which are actually transmitted. But these are actually like the, like if you have the wired connection and you transmit the data, So the wired connection you have like the, let's say that the 4 wire which is going on the 4 transmitter, 4 receiver, but this wire are actually transmitting. But they are not actually having any interference. But when we are actually talking about that this antenna, so let's say like the one is transmitting. So let's say I will name them that like a T1. T1 is like the transmitter 1 antenna. So T1 is transmitting, R1 is there, but it is not only the R1 is receiving, let's say R1 is there, R2, R3, and R4. So all the 4 antenna are actually receiving. But when you are actually transmitting, it was supposed to only receive by the R1 antenna. Similarly, like the T2 is transmitting, all the 4 antenna are receiving. T3 is transmitting, all 4 antenna are receiving, and T4 is transmitting, all 4 antenna are receiving, which is like the 4x4 MIMO antenna system. So here the challenge is like the you have though all those data which are actually coming in the parallel, you have to do the signal processing. You have to separate out like the which data correspond to the which stream, and then you try to add them together. So that is actually like the complicated over here as compared to the wired connection, where the parallel transmitting the parallel data is not a challenge, but in the open environment, it is actually very much challenging. These are some of the antenna you must have seen, like this Wi-Fi router you must have seen, like now the Wi-Fi router has the such antenna. Sometimes it is actually like the packed inside, where like the multiple antenna are there. So if you compare with the base station coverage, like in the 4G, we say like we have like the different sector. We have like the 120-degree sector or the 90-degree sector, and within the sector, I will have like the one beam which is actually forming, and within this one, either like the way actually we actually cater that the different user is like we are transmitting at the different frequency, or we are actually transmitting the signal at a different time instant, but the my beam width remains that the same. Whereas like the massive MIMO antenna, which could be like a part of future 5G, it will have like you have the many number of the antenna which are actually present on the transmitter side, and you can actually form the dedicated beam towards the user, which was actually not possible in the 4G or the current 5G system. But in the future 5G system, this was actually predicted like it will have like the bisim system where the beam, individual beam will be formed toward the user, and that will actually provide like the higher data speed. So to have that one, instead of like the each individual user connected to the main base station, there could be the many sub base station, like the building has the one sub base station, this building has the sub base station. These are the base station. So this main base station will be connected to the sub base station, and then sub base station will be connecting to the different user. So what you can have then you can have the one dedicated beam which are actually going towards like the sub base station, and then this sub base station will be actually connecting to the devices which are actually present on those surroundings. So the word actually there's one thing that is called like the full dimensional MIMO antenna. So if you see here, let's say if the user that are actually present on the same surface over there or the same elevation, same azimuth plane, then you can actually have the dedicated beam. So these are actually dedicated beam towards like the user. But the people are actually thinking that the one step ahead, which says that the full dimensional MIMO. So you can have the beam forming either in the elevation plane, or you can have the beam forming in the azimuth plane. So this is actually like the azimuth plane, and this is actually elevation plane. So you have such a large number of antenna, so that if you want, like the user is actually, let's say, sitting in some building, so you can have the dedicated beam towards like the individual user. Or let's say if they are present on the same area, same floor, then you can have actually like this beam which is actually forming. So if your base station can satisfy the such requirement, then it will be called like the full dimensional MIMO antenna system. So now actually before going to like what is the actual MIMO, let us understand that the why we are actually going on the MIMO antenna system. So we will start with the very basic example. So we know that this Shannon-Hartley theorem, which actually predict like what will be my channel capacity, and this channel capacity is like the bandwidth. This is B log 2 1 plus S by N, and S is actually like the signal to noise ratio. So see the channel capacity bandwidth S by N is like this average signal average received signal power, this is S, and N is actually like the average power of the noise. So Sn is like the signal to noise ratio. So if I know that the signal to noise ratio, I can actually predict that what will be my channel capacity. So take like the one example, if my SNR is 20 dB and I have been given the bandwidth of the 4 kilohertz, this is for like the very standard telephonic system. So if I see like the S by N, if I convert this 20 dB in the linear, it is actually like the 100. So if I calculate that what will be my channel capacity, this is 4 log 2 1 plus 1 by 100. And this comes like the 26.63 kilobits per second. Or it could be vice versa. Let's say if I know like the what will be my channel capacity, which is like the 50 kilobits per second, and the bandwidth available to be 10 kilohertz, I can calculate like the what should be my SNR ratio. So these are actually like the very standard example of the how to calculate the channel capacity from the SNR or from the bandwidth. So the way we actually have the let's say like the we have the start with like the CISO system, which is called like the single input single output, and most of the conventional system are like the single input single output system. So I have the one transmitting antenna and I have the one receiving antenna, and the way the environment is actually modeled, that is actually modeled with like the channel response called the H, and which is the function of the T and the tau. So T is actually giving like the at what time instant you are looking, and that tau is actually giving the delay. So let's say if the channel response is time and the frequency invariant, like there's no time delay in the signal, and with the time the channel the environment is not changing. So just to simplify the problem, we are considering like this will be time and frequency invariant system. So h t tau we are actually assuming to be the constant h. So y, which is actually like the received signal at the receiver antenna, will be h times x. X is like the what is the signal that is transmitted from the transmitter. H is like the channel response. So h times x will be like the signal which is coming. But along with that one, there will be some noise will be added because of the environment. So my y will be hx plus n. So y is the received signal and x is transmitted signal, and n is actually like the additive Gaussian noise. So by CISO system, the channel capacity will be log 2. So here like the bandwidth term we have just normalized. So it will be like the whatever the channel capacity I will be actually getting, that will be bits per second per hertz. So it is like the log 2 1 plus PT is actually like the transmitted signal. If I multiply with the H mod square, that will be like the signal received by the system, and divided by the sigma n square, which is actually giving you the additive Gaussian wide Gaussian noise. So this is like the 1 plus PT by sigma n square H mod square. So this is actually like the if I have the single antenna transmitting and receiving, then what will be my channel capacity? So this y equal to this hx plus n, which is actually CISO system. So let's say like the if I have the very good signal to noise ratio, okay, let's say like the 20 dB, which is actually like the on the linear scale, it comes to be like the 100. So in that case, it is like the log to 1 plus 100, which will be, I can ignore that one over there. So it says like let's say like your received signal, transmitted signal, and then multiply with the h square, so which is very high. So in that case, I can actually assume like the higher signal to noise ratio. In that case, I can just ignore this one, and the channel capacity will be log 2 pt by sigma n square mod h square, and which will be 2 log 2 base h plus log 2 SNR. So this is here actually this is like the very important point. Why actually we are going to MIMO? If you see that now if I have to increase the channel capacity in the single antenna system, which is CISO system, I have the channel capacity which is log 2h and plus log 2 SNR. So SNR is, it says like the if I will increase the SNR by the 3 dB, then I can increase my channel capacity only by the 1 extra bit per second per hertz. Okay, if you are increasing SNR by the double or on the 3 dB, the channel capacity will be increased by the only 1 bits per second per hertz. So that is like the if I am working more on this SNR, I cannot achieve much. So the channel capacity, if I have to increase channel capacity, actually like the your data speed, which you actually talk about, I have to work on the this H, which is like the my channel response. It's a log to H. So now how to actually work, because like if you have the single antenna system, you don't have the much option to play with this H. But if we actually go for the MIMO antenna system, so the channel matrix H will be actually like the different over here. So these are actually like the my multiple antenna on the transmitter side, and these are actually like the multiple antenna on the receiver side, and this becomes like the my channel matrix. So here my response Y, which will be actually like the signal which are receiving on different data, which will be H times X plus N. And if I actually do the analysis, I can actually calculate like the what will be my channel capacity. So let us first understand like the what are this H. So now earlier H was the single number, but now this H is actually in the form of the matrix, and this H11 T tau H11 is actually showing like the what is like the my channel response if my antenna 1 is receiving and it is transmitted by the antenna transmitting antenna T1. H12 is like the received by the R1 and transmitted by the T2. H1 empty is like the received by the uh, antenna received by the R1 but transmitted by the empty. So empty is like the total number of transmitting antenna, and MR is actually total number of receive antenna. And so these are actually like the what will be dimension, and H which will be like the MR times empty. MR is like the number of receiver, empty is number of transmitter. So how the each antenna are correlated with the other antennas on the transmitter side, which is actually governed by this matrix, and which is like the my channel response matrix. So CISO, it was like the log to 1 plus PT by sigma and H square. This was the CISO system. But if I will, because we have gone to the MIMO system where it become the matrix. So if you do smart mathematics over here and try to calculate like the what will be the MIMO channel capacity, it will be log 2 determinants of IR, which is identity matrix, plus PT. PT is like the transmitted power, but this total transmitted power is the PT. So the number of antenna are empty. So the total power which is transmitted, that will be divided by the each individual antenna, and so it will be the transmitted power by each individual antenna, that will be PT by MT sigma n square H into H Hermitian. Here the single CISO system, it was the H square, and here it is like the H into the H Hermitian over there. So that will be your MIMO antenna channel capacity, which is H times the HT. So Hermitian means like it is like the transpose and the complex conjugate. So that will be the H into H Hermitian. So currently we are assuming like your antenna, like the power is equally divided, and you don't have any channel state response information. So if you assume that your channel is independent and identically distributed, what does it means by like how the antenna 1 on the transmitter and antenna 1 on the receiver, like the T1 and R1, the way they are correlated, and the way the T1 and R2 is correlated, or T2 and R2 are actually correlated, they are completely independent. And how the signal are actually reaching from the one antenna to other antenna are also the identically distributed. Like what is actually meaning is like we are assuming that this matrix, which is not the sparse matrix, they all element are actually like the non-zero element, and they are not correlated also. So that is actually the meaning of the independent identically distributed Gaussian variable. So in that case, if such condition is achieved, C MIMO will be M times the CISO. M is like the number of transmitter and receiver antenna, which we are assuming is like they are actually equal. MR, M is the MR plus equal to the MD. So in that case, the C MIMO will be M times C. So it means like let's say if I have be talking about the 4x4 MIMO antenna system, and if it is like the independent identically distributed, I can actually increase my channel capacity by 4 times. And if it is like the 8x8 MIMO antenna system, I can increase my channel capacity by 8 times as compared to the CISO antenna. It is not like the 8x8 is like the 64 times you increase the channel capacity. No, it is like what is like the M is like the MR into MR are equal to MT. So it is actually like the one side, whatever is the antenna on the transmitter receiver side, if they are equal, so then C MIMO will be M times the CISO antenna. So if I compare, like, let's say, like, if I have the CISO antenna system, I have the MIMO antenna system, and I'm currently assuming that this is independent and the identically distributed channel. So let's say, like, if I have I want to transmit the data with the 1 Gbps speed, and I have the channel which is actually having the 20 dB SNR. So if you use the single antenna system, this CISO system, I need a bandwidth of the 150 megahertz to get the speed of the 1 Gbps. But if I have, let's say, the MIMO antenna system, and I have the 6 element, I can actually reduce like my bandwidth requirement to 1/6, and I need only like the 30 megahertz over there. And these are like the ideal case, but even though, let's say, that there is a small correlation in the channel, is still like my bandwidth requirement is not that significant. It is like the, let's say, 40 megahertz as compared to the CISO system, where the CISO system is actually required 150 megahertz of the. So bandwidth, so it's like the for CISO system you require the 150 megahertz of the bandwidth, whereas like the MIMO system you need the 30 megahertz of the bandwidth. So it's just like the 30 megahertz of that. So this actually give you that the knowledge, like the why we are actually going at the more number of antenna, because ultimately it is actually increasing my channel capacity, and channel capacity is actually related like the, you talk about the data speed, or you say that the going from the 4G to the 5G, where actually like the 100 Mbps to we are going to 10 Gbps. So there one more critical point is like the SNR. So this one is like the on the x-axis it shows like the number of antenna that is present on the x-axis, and on the y-axis we have like the what will be like the my channel capacity. It's like the bit per second per hertz. So it says like if you have the SNR 0, so this one is SNR 0 line, and it says like the, let's say like the, if you have the requirement of the some some, if I am using actually, let's say that the one antenna and my SNR is like the 0 dB, the channel capacity actually I can get is like the very nominal. And even though if I'm increasing my number of antenna, I don't get the significant improvement in the bandwidth. But if my SNR is let's say 20 dB or the 30 dB, you see that the one element bits per second per hertz information, let's say it is like the close to like 6, it is almost actually reaching like the 60 bits per second per hertz. And if I have the SNR of the 30, I have even the larger slope. So it is not that the higher the SNR, anyway you'll be getting the more bits per second per hertz. But if you have the MIMO antenna and the SNR together, then you will have the very significant change in your channel capacity. So this is just like the example of like if you have the system called like the CISO, C MIMO, CMO. This is like the single input, multiple output, and it is like the multiple input and the single output. So if the green line is actually like the CISO, and the black line is the MISO, which is actually like the multiple input but the single output. So if you have the one receiver antenna and you have the many transmitter antenna, you don't get any advantage in the channel capacity. If you have the single transmitting antenna but the multiple receiving antenna, you still get some improvement, but that improvement gets saturated after some time. But if you have the MIMO antenna, you will actually have like the very good number of the improvement in the channel capacity will be very significant. So how to actually get this? Because I said like we have assumed like it should be the identically distributed. The channel capacity should be identically distributed and independent. So to have such thing, like in 3G communication or the conventional 4G communication system, what we prefer that we should have the line of sight communication, like from the base station If you are in the line of sight communication, you will have actually like the very good signal strength and then very good channel capacity. But that is not the case of the MIMO antenna system, because if you go to the MIMO antenna system and if you have the line of sight of communication for the one particular, let's say, uh, channel coefficient, like the H, which is actually, let's say, I have the some antenna which is transmitting from here, some antenna, but that the one of the antenna is actually directly receiving the signal from the your transmitting antenna. In that case, that coefficient in the matrix will be actually very much large, and the other coefficient on the matrix will be actually like the smaller. So the matrix which I said like the it should be the identically distributed and independent. It means like the you are saying that the channel matrix is the full rank matrix. But if you have the line of sight communication, your matrix will not be the full rank matrix, and in that case the matrix become the sparse matrix, and you won't be getting like the C MIMO is like the M times the C antenna. Okay, so in conventional system, line of sight is preferred, but MIMO antenna system, non-line of sight communication is preferred, just to get the independent and identically distributed. So non-line of sight communication is the key parameter for the MIMO antenna system. So this is same thing. Okay. Now, as an antenna engineer, what are actually like the challenge here in the MIMO antenna system? So as a antenna user, like the if you see the way the signal processing people work, they assume like the all those transmitter which are actually like the on the transmitting side, or the all the receiver antenna which are on the receiver side, they are not correlated. It means what we are actually saying like the if my T1 is transmitting, T2 is transmitting, but there is no correlation between the T1 and the T2. Like there should not be any possibility like the T1 is transmitting and the T2 will receive, or the T2 is transmitting, T3 will receive, or similarly like the correlation between the R1, R2, R3. So they assume that this correlation on the transmitter and this correlation on the receiver, they will be correlated. Okay, so signal processing people, they only work over there with they say, okay, this is not the case of the independent identically distributed. Instead, like they work more on the channel, whereas the antenna designer, they work more because there are the strong correlation between the antenna which are present on the one side. It is could be either the transmitter or it could be either the receiver side. So the channel response matrix that is actually changed from the H, which will be R, which is like the R receiver side, and the RT, which is actually the transmitting side, and HID. So the signal processing people, they assume like that these two matrices are like the ideal matrix, and this one is like the non-ideal matrix. Whereas that the antenna engineer, we assume like that this is like the ideal matrix, and these two are the non-ideal matrix. But the real system, they all three will be like the non-ideal matrix over there. Okay. So as antenna engineer, we try to focus more on the this element and this element of the expression, which actually govern my channel response. So as antenna engineer, when you actually design any antenna, MIMO antenna system, the conventional antenna parameter you have to anyway look, which are actually like the reflection coefficient, input impedance, radiation pattern, diversity gain, radiation efficiency, and then the polarization. Whereas that we have the some other parameter, which being that the MIMO antenna system, if you are designing, you have to see which is like the envelope correlation coefficient, channel capacity loss, total active reflection coefficient, and the mean effective gain. So these four parameters are additionally required as compared to the conventional antenna parameter if you are designing any MIMO antenna system. So what are those parameters we will discuss? One is like the envelope correlation coefficient. So what actually it says, if you see, this is the integration E theta I, E theta j complex conjugate, and then I'm integrating over a volume which is actually d omega, and then the E phi I, E phi j omega integrating again at the d omega, and then this is the square root E theta I mod square E phi omega mod square, and then we are actually integrating over the domain d omega, and this E theta j E phi j taking the mod square and in the d omega. What actually is the physical significance of this one? So it says like that you are supposed to calculate the correlation between the two antenna radiation patterns. So antenna radiation pattern, I have the three term. One is like the ER, E theta, and the E phi. Okay, and mostly we actually assume like that the antenna is radiating and it is satisfying the plane wave condition. So you won't be having the ER component because the wave is actually propagating readily outward. You don't be having the ER component because of the plane wave condition. So you have only the E theta and the E phi field present. And E theta and E phi field which are actually present. So I assume that there could be the two antenna because it is the MIMO antenna system. So is between these two antenna, is there any correlation? So how will you calculate the correlation? You will take the ith antenna and the jth antenna and see like the ith antenna E theta field. So this is E theta I, and multiply the complex conjugate of that one with the E theta j field. Okay, so at any point in space, so this gamma is actually, the omega is actually representing the theta and phi, and the d omega is representing the d theta and d phi over there. So what I'm actually representing the E theta I at any point in the theta and phi, and at that point I will actually multiply with the E theta j. So these are the one product, and the other product is the E phi of the ith antenna with the E phi j, and then I will integrate over all the theta point in space and all the phi point in space, and try to see that is there any correlation, and then whatever the correlation I will actually normalize that one. This is like the total electric field that is radiated by the ith antenna. This total electric field radiated by the jth antenna. So this is like the complex, this term called the complex correlation coefficient, and if I take the mod square of this one, that is called the envelope correlation coefficient. So we try to calculate like what is the envelope correlation coefficient of any antenna. So now we have to actually reduce this envelope correlation. The correlation should be minimized to have like the channel matrix which should not be sparse. So let us assume like what is actually like the basic concept to design any MIMO antenna. So I have this very standard element. I am actually taking like the dipole antenna which is oriented along the x. So if any dipole antenna which is oriented along the x, I will have the radiation pattern which will be in the azimuth plane, which is actually in the xy plane. So these are actually in the xy plane, and I have the element that is along the z. So I should have the null along the z, and I should have like if I will actually see the response in the xy plane, I will be actually getting like the omnidirectional radiation pattern. And if I will take like the pattern in the yz plane, I will be actually getting like the pattern 8 that we say. And there the two component also we see like what is the E theta and the E phi component. So if I see the radiation pattern in the xy plane for this antenna, so for this antenna, if I see in the xy plane, I will get the omnidirectional pattern, and the component of the field which will be actually present because this is dipole antenna. So you will have like let's say field line starting from here, and then it is going. So I will have the E theta field which will be actually present. So these are like the red one is like the E theta field which is actually present, and I have the E phi component which will be the cross polar component here, which will be actually like the very small. Similarly, if I will take the yz plane, so I have the E theta field which will be actually present, but the pattern will be like the 8, and my black one is like the cross polar. Now let's say if I have the same dipole element, but it is actually present along the z. So along the x, so what I will get? I will get null along the x. I will get the omnidirectional pattern in yz plane. So if I see here in this one, this is yz plane if I will cut, so I will get the omnidirectional pattern. But the field lines which will be there, the prominent, So because the elements are actually along the X, so I will have the field lines which will be actually going like this one. So I will have the E phi field, which will be actually prominent here in this case. Or here the E phi field is actually prominent, and these are actually like the my cross polar, and which is actually like the E theta. Red one is the E theta component, and these are E phi. Now let's say if these two dipole, they are actually placed in a space, can they work for the MIMO antenna? And then whether the correlation will be very small. So I have the three direction, which is like the X, Y, Z, or I can have let's say like the, just for the assumption we can take like the along the X, Y, Z, or I can take the minus X, minus Y, minus Z also. So let's say along the Z direction, if I'm trying to calculate the correlation coefficient. So along the Z, this dipole is not radiating. Okay, first dipole is not radiating. I have the second dipole which is radiating. But if I will take the cross product of the correlation coefficient, which is actually given here, E theta, E phi, and E phi, E phi I and E phi j. So one dipole is radiating in that direction, and the other dipole that is not at all radiating in that along the Z direction. So because these are my Z, this is YZ plane, and this is like the along the Z. So here, if you see, this dipole has like the high value of the field intensity, but here there is no field intensity along the Z. So I will not get the any correlation along the Z direction. Now if I will see along the Y, along the X, so along the X, this is like the thing. So the along the X, this dipole is not radiating, which is actually 0, but this dipole is actually radiating along the dipole, so it is actually maximum. But if I take the product of these two, that will be 0. So this is like the along the Z and along the X. If I try to calculate the correlation, they both are not radiating, and the correlation is 0, and that is the word used by the MIMO antenna communities like the pattern diversity. Okay, your antenna is not radiating at all, so this is like the called the pattern diversity word, which you have heard. Now if I see the antenna element along the Y, so along the Y, if you see, this dipole is also radiating, and this dipole is also actually radiating. Both the dipole element are actually radiating along the Y. So if both will be radiating along the Y, then if I see here, let's say this is YZ plane. So this element is radiating, this is like the YZ plane at 90 degree I'm looking, and this is another element 90 degree, they're radiating. But now correlation is like the, here E theta is actually maximum, whereas the E phi is almost like the 0. Whereas the second element, my E phi is maximum, but the E theta is actually 0. So though both the antenna actually radiates in the same direction, but the correlation, if I try to calculate the correlation, the way the expression is that the E theta I times the E theta j. So here the second element, E theta I is significant, but the E theta j, the second element j is negligible. So this product will be actually again that the 0. And the second term of the mathematical expression is that the E phi I and the E phi j. So here E phi I is the negligible, the E phi j is the significant, but the E phi I is the negligible. So then if I try to calculate the correlation, then again it becomes a 0. So two orthogonal dipole, if they are placed in a space, they are the ideal MIMO antenna element. And that's why like if you see that the many time in the MIMO antenna element, we try to keep one element of the MIMO to the other element of the MIMO, that is like the orthogonal. So this thing is called as the pattern diversity in the MIMO antenna community. They say like this whatever actually we are getting, that is like the pattern diversity. Sorry, polarization diversity. Along the Z and along the X, they have the pattern diversity, and along the Y, they have the polarization diversity. One of the polarization of the electric field is available, but the other polarization of the electric field is not available there. So if let's say if I'm using the three element system, one dipole element is along the X, one is along the One is along the Z, this is along the X, and the third one is along the Y. So these three MIMO antenna element, if they are kept in a space, they will not have the any correlation in a space. Okay, so that will be like the my MIMO antenna system. So the another very important term which are actually which are very much available by this antenna community. So though let's say like the correlation is present, but we have to also see whether the power which is actually coming toward the your receiver antenna system, whether the power is available or not. So though let's say like that these two antenna, which I'm actually saying on the receiver side, they are available and there could be some correlation, but we have to also see that whether the power once it is coming to the receiver antenna, whether the any power is available for that theta component and for that phi component. So the power which is actually coming, so that is like the P average theta and the P average phi. So the once you will actually calculate, so there is like some additional term comes, it is like the chi over 1 plus chi. Chi is actually like the P average theta over the P average phi. So we are actually trying to calculate like the whether the though antenna could be correlated, but if the power is not available, then also the correlation could be small. And that time this is called like the P theta and the P phi. So let's say the power is coming, but what is like the probability that the power is available in the theta component, or what is the probability like the power is available in the phi component. So this is like the P theta and P phi are the probability density function. This is the P theta P phi. So this is actually like the P theta, theta cap, and P phi, phi cap. So this is like the if your receiver system which is not actually like the uniform propagation environment. So if you have the non-uniform propagation environment, the correlation coefficient will be calculated by this expression, which is like the chi over 1 plus chi and chi 1 over 1 plus chi, along with the multiplication of the probability density function. So now as a antenna engineer, you can actually calculate the correlation coefficient using the electric field in the simulating software. Let's say you are using HFSS or CST Microwave Studio, but in practical case, you cannot calculate the field at every point in space. We generally do the field measurement or the pattern measurement in some principal plane like the XY plane or YZ or the XZ plane. But we are not actually calculating the field for the each E theta and the phi values. So all theta and phi value, we don't actually have the expression which actually calculate. So the so so for the practical purpose, instead of measuring the correlation coefficient from the electric field, people try to measure the correlation coefficient using the S parameter, and from this one you can actually calculate this S parameter. Here the 4 S parameters will be required to determine the correlation coefficient between the two antenna. The disadvantage is like they are not very much accurate, but they give actually like the good approximation like what is the correlation. Second thing is like the if you are using this E theta and E phi, so first thing is like the your memory requirement is very high. Like you save the E theta and E phi field for R value of the theta and phi, and let's say that your antenna is actually the broadband antenna, then you will also have the at each frequency point. Whereas the S parameter, it is for the one two antenna system, you will only have the 4 parameters, and if it is function of frequency, so it is only the one array will be only the function of the frequency. Whereas like that this become like the 3-dimensional array, theta, phi as well as frequency, and here it is only the function of frequency. So that saves like the lot of the memory requirement as well. Is there any different formula? Just let me read. So I'm trying to read that. I will just stop sharing because I'm not able to see that the message here. Yeah, is there any different formula to calculate the ECC for the higher port antenna? So ECC will always be calculated between the two antenna elements. Okay. So let's say if you have the 4x4 antenna element, then it will be like the correlation coefficient would be like the antenna 1 to 2, 1 to 3, 1 to 4, the 2 to 3, and 2 to 4. Similarly, like the 3 to 4. It is not actually like the for the 4 antenna system or the 8 antenna system, the ECC will be like the based on the number of the antenna element or number of the port. Uh, I hope that is given that answer. Okay, thank you. Then we have this channel capacity loss, which is actually another important parameter. So if you will be having the correlation, then there will be not like the ideal MIMO antenna system. I said like the ideal MIMO channel capacity is like the you assume that this H matrix, which is the identically and independently distributed, but because of the correlation, you will have the channel capacity that will be actually like the lesser, and this will be like the C loss T and the C loss R. That will be the your channel capacity, and this C loss T that will be minus log 2 RT, and which is actually like this. I will write in the S parameter term. This is minus log 2 IST. ST is like the S parameter I'm actually calculating on the transmitter side of the antenna, and SR is actually like I'm calculating the S parameter for receiver side of the antenna. So if there is the correlation, you will see like the otherwise it will be like the I, which will be like the identity matrix, but because of the correlation, you will get actually like the such matrix over there, and once you will go over here, this will create like the reduction in the your channel capacity. So the channel capacity loss is the other term which actually you try to calculate, and this which is like the C loss T and the C loss R, which is the correlation between these two antenna system. Then another important term which is like the total active reflection coefficient. The total active reflection coefficient is like the even if you are working on the antenna array, sometimes we calculate uh, on the antenna array system also we try to calculate that the total active reflection coefficient. So what is actually the reflection coefficient? Reflection coefficient is like the you are transmitting from the port and whether any energy is coming back to the port. So that is like the reflection. Reflection coefficient is like the ratio of the power which is received by the antenna as compared to the transmitted by the antenna, or the reflection coefficient, or the S11, which there are many things which we say. When we have like the multiple number of antenna, so let's say I have the T1, T2, T3, T4, T5, and I'm transmitting from the antenna T1, there could be the chances it is received by the T2. So if I see the T1, I find out like the okay, yeah, my reflection coefficient is below the 10 dB. Or if I'm operating at the T2, I have the reflection coefficient which is actually like the, because if you are actually individually measuring the element, the way we actually measure, we launch the power at the one antenna element, but we actually make that the other element to be the match load. So I will see that the T1, okay, yeah, the reflection coefficient is very good because my S11 is minus 10 dB. Then I will actually launch the power at the T2, which is, and then I will say that what is the S22, and then I see like okay, it is very good because my reflection coefficient is below 10 dB. But if you are but that doesn't give the information, okay, you are actually transmitting the power from the T1, but the power instead of going to the receiver antenna, that T2, which is actually present on the transmitter side itself, is actually receiving the power. So transmitting from the T1, it is received by T2, or it is received by the T3, or it is received by the T4. Okay, that is not, you are not able to capture. But ultimately, those power is not launched in the system, which actually travel through the channel and reach to the receiver antenna. So to meet out that one, uh, we actually try to find out the total active reflection coefficient. I will launch the power from the 1, 2, 3, 4, whatever, like the all those antenna on the transmitter side, and then I will try to calculate that what is the overall power which is actually coming back to my system. So the way the total active reflection coefficient is actually calculated is like the sigma I times m. M is like the number of transmitting antenna, and bi mod square. So it is like the, I'm actually receiving the power on the 1, I'm receiving the 2 to the, I'm receiving the power on the all the M antenna, and simultaneously I'm transmitting the power from the 1, 2, 3, 4, 5, whatever the M number of antenna. If I have, let's say, the two simplified and two for your understanding, if I have the two element system, so I only earlier we were looking at the S11, S22, but what I have to look is the active reflection coefficient, which is like the B1 with mod square, which is like the power coming to the port 1, and B2 mod square, which is actually power coming to the port 2. With respect to, I'm launching the power at the A1 and I'm launching the power at A2. So these are actually like the, so if I calculate instead of only the S11 and S22, we actually see then the MIMO antenna system, the gamma A, which is like the mod of the B1 square plus B2 square divided by the mod of the square root of the A1 square plus A2 square. This is called like the total active reflection coefficient that you have to do. Yeah, what is the time? Okay, so I will take the 2-3 example of the MIMO antenna system, which will give you that some idea. So I said like my objective of this talk was like more to cover on the basic and give the understanding, because I see that there are many talks which is actually scheduled on the MIMO antenna, but whether like the such a basic will be covered or not. I will give you like the whatever the theory we have proposed is that some channel capacity loss is calculated. Actually, the thing is like that this it pop up and then it disappeared on my screen. I have to again stop doing this one. Let me actually cover two example and then
Yes,
I will
sir.
come back to the chat box. This this 4-element MIMO system. So this is like the 4 elements. So like this is 1, 2, 3, 4, and each individual element are, let's say, the multiband. So multiband is like the, I have the element 1, and the element 1 is like the multiband is like the, I have this monopole antenna. This is actually providing me one band. Let me just see that. Okay, that is not given. So let me just explain. So I have the 4 band because one is like the monopole is actually giving that the one band, then this SRR is giving me the other band, and then the interaction of these two are also giving me the 2 additional band. So this is like the 4 band over there. That is not the important part. Is like the what we are doing to get the MIMO. So to get the MIMO antenna, if I compare the element 1 and element 2, if you see that they are orthogonally placed, the way actually I have shown the example in my theory, if you have the two dipole which are orthogonally placed, they will actually give pattern and the polarization diversity. So 1 and 2, they are like if I see this one is like my 1 and this is my 2, so 1 will have the null along this direction, 2 have the null along the this direction. So they will have like the pattern diversity, and like the out of paper they both will be radiating, but their polarization will be actually different, so they will be actually providing the polarization diversity. So 1 and 2 are actually uncorrelated because of the orthogonal placement. 1 and 3, they are actually again like they are actually in the similar direction, like the 1 and 3 both are actually aligned in the similar direction, but they are actually far apart if I see that these are actually having like the sub distance from the 1 and 3, and that is called what is called the space diversity. So in MIMO antenna system, you are basically having the three type of diversity. One is the space, pattern, and the polarization. So 1 and 2, they are actually having the pattern, the polarization diversity, whereas 1 and 3 is having the space diversity. They are actually having somewhat away from in the space. So if you see the particular direction, they will have the some phase delay, and they will actually try to cancel each other. And 2 and 4, again like the space diversity, 2 and 3 are pattern and the polarization diversity. So these are actually like the my S11, if you will be looking over here, and these are like the by S21, S31, S4. If I'm pumping the power from one, is that the correlation between the 2 and 1, 3 and 1, or the 4 and 1? So that is like the thing which you actually are getting. All are the correlated with like the S41, S31, and S21. They are below like the 20 dB over there. Though because of like the time constraint, I'm not actually showing all the result, but you can actually go and you can actually find out on those paper which we have published. Here, if you try to see that the correlation coefficient, so this antenna is actually operating, let's say like the 1.8, 2.5. So if I see here 1.8 and the 2.5, the correlation coefficient are actually like the very small. Okay, it is the correlation coefficient is between the 1 to 1 3 and 1 4. I said like the you have to calculate like uh, row 1 2, row 1 3, and the row 1 4. They should be actually like the at least the standard is like the 0.05, but the if you see here it is like the 0.0, it is lesser than the 0.01. I said the 0.05 is even the good number, but the correlation is like the less than 0.01. Here this is another example where like the I have again like the these are actually like the monopole antenna which are actually just have been actually like the bent over there so that it actually reduce the space, and then they are loaded with the this CRR. The advantage is here the element I have actually put like the some extra metal lines over here, and this metal lines actually provide me two things. One is like the when you receive the signal, you should have some common ground. Where I think most of the MIMO antenna system, they are not talking about the common ground. But like if you are really wants to use your MIMO antenna system in the practical system where actually you have the receiver chain and the signals are actually received, you should have that the some common ground. So one advantage of this element is like the you have the common ground, so that actually give me the one requirement like okay, yeah, you have the common ground that will be can be used for the practical application. And second is like the because of this common ground, let's say if I talk about the element one, they are trying to bend the radiation pattern uh, towards the one particular direction because this is working as a reflector. Okay, so let me go with the uh, so here if I'm feeding to the element 1, the radiation pattern is in this direction, which is actually like the this direction that it will be radiating. Antenna 2 will be radiating in this direction. Antenna 3 will be radiating in this, and antenna 4 will be radiating in this direction. By putting this metal lines, that is also helping me to get the pattern diversity. So these are actually like the pattern diversity. I'm getting the different pattern because of this MIMO antenna system. So these are some numbers which is actually given the row E12, which is actually coming very small, the 0.0005. Okay, I said that the requirement is even 0.05 is the good number. And because this element is actually loaded with the SRR, and because of this, CSRR, complementary split resonator, I'm getting like the one additional band. So not focusing more on the additional band because the talk is more about the MIMO, but you have to understand that what we are actually getting because of the putting this one. So these metal lines are actually put to get polarization. Sorry, in this case, it is the pattern diversity. Yeah, I will take one more example and then I will take question. These are actually like a very unique thing which we actually try to develop the two element MIMO system. The concept wise, it is actually like the very good. So the way what we are actually doing, let me first understand the concept here. You have this patch element. Patch means like it is only the metal patch, there is no ground. This is one patch which is actually present. And I have this one dipole here and that dipole here. This is dipole 1, this is dipole 2, and this is like the my x, y, and the z axis. So if this patch would not have been present, this dipole 1 would be radiating the omnidirectional radiation pattern in the xz plane, and dipole 2 would also be radiating the omnidirectional pattern in the xz plane. Now, once we are actually putting this patch, because of the presence of the patch, what will happen? The energy which was actually, so dipole 1 will be radiating more on the minus x direction and dipole 2 would be radiating more on the minus dipole 2 would be radiating more on the plus x direction. The contribution will be less along the minus x for the dipole 2, and though they both will be radiating along the plus z and the minus z. Okay, so if I see the comparison, dipole 1 and the dipole 2, they both will be radiating on the plus z, whereas like they will be radiating less on the minus z, and they will be radiating on minus z and plus z. Now, what now we are doing, we are actually feeding these two dipole elements with the different phase. It's a dipole 1 we have fed with the 0 phase and dipole 2 with the 36-degree phase, or the 72-degree phase, or the 108 or 140 or 180-degree phase. If I see the active reflection coefficient, it remains to be like the same over there. But if I see the pattern response, so the pattern response is like if they both are actually fade, like the phase difference is 0, the way I have actually given, they both will be radiating along the plus and minus z, but only one will be radiating along the plus x and another will be radiating on the minus x. And that you can see here, if the phase difference is 0, you have the more radiation along the plus z and the minus z, and lesser radiation, but they are significant still along the plus x and the minus. But now if I will keep changing the phase difference, you find out like the radiation which was happening along the principal plane, along the z and along the x, now it is actually shifted to the some other direction, which is like the theta 45 degree and the theta 135 degree. Similarly here, so if I compare this element when the side is 0 and this element with the side, the phase difference is 180 degree, there is like the pattern diversity over there. Okay, and that we try to achieve in this antenna. So this is like the one dipole element which is actually over here. Just this CSRR loading is only actually making the dual band, that is not important. So it would have been radiating along the, let's say, one element, because of the presence of this ground, it is radiating. So this is x, so this is radiating along the plus x. Now I have to feed that the two element antenna system. So I have designed the two set up the power divider, one set up the power divider which are actually giving the equal phase output power, and here the equal power is there, equal division is there, but the phase shift, this D line is actually used, and which is providing me the 180 degree phase shift. So the overall antenna will look like this one. This is my original ground, this is my port 1, and this actually feed to this system, where actually like both the element are fed with the same phase, and the port 2, one element is fed with the 0 phase and another element is fed with the 180 degree phase. And by doing this one, what actually like the major changes we actually obtained, you see over here, I will be getting like the more radiation along the plus z and minus z and the plus x and the minus x. But the moment I'm actually changing the because of this phase, at pole 2, I'm actually getting the radiation on the some other direction. This is like the some fabricated response. I will actually stop over here. I want to take more questions, otherwise the session will be in it is already. Please keep posting your question over here. So that I'm just have stopped my share because I cannot read the screen and the chat box together. So yeah, ECC part I have answered this, sir. For CCL, how the channel capacity loss is calculated? Practically, as the user is in the transmitter receiver side and the channel is the unpredictable. For the channel capacity loss, I said that you will calculate like the S parameter, and this I said like the channel capacity loss as antenna designer, we are looking like the how the antenna correlated at the transmitter and the receiver side. We are not looking the model of the channel. We assume like the channel model is the ideal or whatever be the number. But because of the correlation of the antenna and the transmitter and the receiver side, there is the the overall the channel matrix response will be changing. So channel capacity loss, the contribution is only how the antennas are correlated at the either on the transmitter side or the receiver side, and those you calculate from the your S parameter, which is actually like the log 2 I identity minus S transmitting and S transmitting Hermitian. I hope you understood that one. So what is the minimum distance? The minimum distance for the space diversity should be at least like the lambda by 2. Okay, should not be lesser than the lambda by 2 to have that one. All this the MIMO parameter like the ECC, MEG, CCA tasks are always measured between the two port only, no effect of the other port. So when you measure, you assume like the other port are actually other port are terminated with the match load, and match load is the condition is like the like the whatever what actually match load give the condition is like the if I'm actually transmitting, let's say I have the 4-port system and I'm measuring the correlation coefficient between the 1 and 2. So antenna 3, let's say power I'm feeding at the 1, and if the power is going to the port 3 should not be re-radiating. That is actually our objective. I should only be looking like if I'm transmitting the power at 1 and if I'm transmitting the power at 2, what is the correlation? Whereas like the 3 should not be participating in that activity. So that is actually like the thing we try to do. But when you are actually calculating that the torque, the overall effect what we are actually trying to measure is like the when the all the port are actually transmitting, what will be your overall response. So that's why like the for the torque calculation, that is not the case. What is the effect of connected and unconnected ground? Some researchers do not use the connected. Yes, that is actually like that I mentioned, that is very important point, because once you are actually receiving that, let's say that you have the 4 antenna system, you have the 4 signal which you are receiving. How you are actually trying to make the reference between these two signals. Okay, to make the reference between these two signals, you should have the common ground. So ultimately, though the many researchers are actually publishing paper where the common ground is not actually given, but if you want to really use that antenna element in your practical system, any transceiver system, you should have that the common ground. There should be some common reference how actually you will judge that the okay, as compared to this reference, how much is like my voltage, how much is my phase. So that's where like the word common ground actually comes. So what are the practical feasibility of the super wideband MIMO antenna? Super wideband, I don't know. Like the wideband antenna is actually preferred. Let's say like that if I'm looking for this 5G communication, which is now covering from the 3.4 to 4 gigahertz, or sometime, so that is like the based on the which country you are actually operating. Sometimes you can design the 3.3 to like the 5 gigahertz, which will be actually catering like the all the band. So depend upon like the what is the your requirement, you can actually create that antenna. The word super wideband does not actually have the any meaning like the what actually you are looking. It depends upon what is your requirement, and based on the requirement you try to design the antenna, whether it is like the you are either designing for the base station antenna, or whether you are designing for the mobile handset antenna, or you are designing for the Wi-Fi router antenna. Okay, so let's say if we have the Wi-Fi router which only operates like the very close to, let's say, 5.5 gigahertz with having the very limited bandwidth. Even though if you have designed the very wideband antenna and you are actually using that one in the Wi-Fi router, there's no point actually. You are just actually have the design, but you are not using the other frequency band. So based on the requirement, you have to design that antenna. Yeah, if you have the more question, you can actually post, or otherwise, if the organizer can unmute the participant who wants to actually talk.
Sir, one more
Oh,
question.
yeah.
What is the wrong if we get minus 15 dB coupling for space diversity where we put antenna below lambda by 2 distance?
There's no problem if you can really get like the minus 15 dB coupling coefficient. If the antenna element are really less than lambda by 2, that is good. Like, that is not undenied over there. People are actually working like the smaller element antenna or the compact antenna, and they try to actually get that one. Okay. So, but like the if you are keeping the lambda by 2 away, generally they are actually providing the good coupling. But if you can still get very good coupling of minus 15 dB, then that is good. How many maximum number of antenna in MIMO? If I said the higher is the better, that is actually, let's say like this mobile handset, I said that the 64 element will be better, but whether you can actually pack the 64 element in the mobile handset. Okay, so your mobile handset will not can cater the 64. Generally, like the people what they have designed is like the 8 element currently they are using on the mobile handset. Yeah, but on the exchange side, people are actually targeting that they will be going the 64 or the 128 element antenna. Or 128 times 3 is 128 uh, in the one sector, and then they can actually go on the three sector, four sector. That will be 128 multiplied by 3 or 4. So that will be actually the antenna. On the base station, you don't have the constant of the space, but for the mobile handset, you have the constant of the space. So you will actually choose number of element accordingly. Yeah, there is nothing wrong if you can actually get the space diversity even with the lesser than the lambda by 2, if your coupling is even smaller. But you have to see that the coupling is not because of the polarization or the pattern diversity. It is only coming because of the space diversity. Then only like the whatever the number you are suggesting is good. Any other comment?
Participants are requested to ask the question if you have any doubt. Sir, I think there are no more questions.
Okay, then so thank you.
Simi Chaudhary. Sir, one more question is there.
The maintenance system only applicable for mobile application, or we can use for the TV channel. Uh, the MIMO antenna system, when you are actually talking about we have started with like the transmitter and the receiver. Okay, with like you transmit and the you receive. Whereas like the when you are actually talking about the TV channel, these are mostly not actually communication. It is the broadcast. So broadcast is like you are just transmitting the signal, and the receiver signal are, you are not actually trying to develop the two-way communication. It is actually like the one-way communication only. Okay. So I have actually shown you like if I have the CISO antenna, if I have the MISO antenna. So from there you will get the idea. Okay, under what condition if the broadcast antenna you are using, you get an improvement. Generally, for the one-way communication, you generally don't try to put such constraint over there, make the antenna complicated. there is no actually perfect guideline from the lambda by 2 which you are actually writing. It is only thing is like the if they are actually lambda by 2 away apart, and if they are radiating in a space, the phase difference between these two antenna will, once there the signal is actually propagating in a space, they will have the significant difference. Okay, if they are the lambda by 2 apart. The similar way, like the if you go to the array antenna and we say okay, the antenna element, if they are actually lambda by 2 apart, they are treated to be good because the mutual coupling is at the very small. So just to avoid that the mutual coupling, the lambda by 2 number was actually given. What is MIMO and the maximum? So MIMO and the massive MIMO, massive MIMO, when we are actually talking about, there could be so here then when we actually correlate in the MIMO antenna system, we are saying like the individual antenna element, they are actually uncorrelated with the 1 to 2 or the 1 to 3 or 1 to 4. Whereas the massive MIMO antenna, you will actually form the array. Let's say I have like the 64 element array, and in the 64 element, 10 element will come together and form that the one array beam, and the 10 element will come and form the array in the some other direction, and these two antenna element will be having that the, let me show like the one of the picture, so that will be having the more clarity. Yes. So this was like the one of the 5G base station antenna. So if you see here, like I have like the many number of the element which are actually present. What we can do, this element, let's say 1 cross 6 element, this element can form the beam toward the one direction, and this element on the horizontal side are the other elements which are actually present, they can form the beam in the some other direction. Okay, so if you have, so these are not actually one or two elements, these are actually like the massive MIMO, which are actually having like the more number of element, and element is together are coming together to form the beam in the particular direction, and that is actually like the word that is called like the massive MIMO antenna. So here like the, these are like the, let's say the four elements are there, and within the four element there are four more elements are there, and these are actually forming like the one particular beam, and that set are forming the beam in this direction. So these are actually like you have the parallel beam, but they are also coming together to form the array. So that was actually logic of the passive paper. Which book can provide insight designing the antenna concept with respect to for the MIMO antenna? I don't see like the, well, I have not followed the book. These are mostly like the journal paper which we are following. Thank you. My email ID is the kvs@iitk.ac.in. So Anaiza, can we end this session now?
Sir, I think now there are no more queries.
Uh,
Sir, on behalf of EICT Academy and MNIT Jaipur, thank you very much, sir. The session was very much informative, and for sure this will be useful to all our participants, sir. Thank you
thank,
very much once again, sir.
thank you. Thank you.
Dear participants, the next session will start from 11 a.m. You are requested to kindly join by 10:45. Thank you.